last time we introduced the microcanonical ensemble, which describes an isolated system for any given Hamiltonian, so it is very general. I'd like to illustrate this by calculating the properties of an ideal gas using this. So in the, as you recall, what you want to calculate first is the volume occupied by the ensemble in gamma space. So we'll call it gamma of E. It's just equal to the integral over everything, the 3n of x, the 3n of p times the density function that defines that ensemble. But in this case, it's a uniform distribution as long as the energy lies between given limits. So it's just for each x you integrate over the volume V, for this you integrate such that the Hamiltonian of p and x lies between E plus some tolerance and E. And let's calculate this and try to deduce the thermodynamics. The thermodynamics is given by saying that the logarithm of this term is the entropy. Now, one can calculate this small e. I omit the v dependence for convenience. Let this be defined as integral d3n of x integral d3n of p for hpx less than e. And then gamma e is equal to sigma of e plus delta minus sigma of e. And if delta is just a tolerance, it is usually very small. So this is approximately equal to delta is equal to d sigma e dE times delta. So all we have to do is to calculate sigma. Now sigma, is equal to this term just give you a factor, v to the n, right? This integral just gives you v to the n. And this integral is times integral dp1 dp2 times dp3n. There are 3n degrees of freedom. So that p1 squared plus p2 squared plus up to plus 3 p to the 3n squared divided by 2m is less than e. Now, of course, you would notice this is just the volume of a sphere. You integrate over all the coordinates subject to that the sum of the square is less than a certain value. So that's just volume inside a sphere. So if I let omega n r equal to the volume of an n sphere, a sphere in n dimensions, then sigma e is just equal to v to the n times omega. The dimension is 3n, and the radius r is equal to 2m e into square root. So this is a so we to this we need the volume of a sphere in n dimension. You can just I'll just quote the answer. It is derived in the book, so I'll not go through it. And the result is omega n of r. Of course, it is, you know, it's proportional to r to the nth power. So all you need is a constant in front. And that constant in front is equal to pi to the n over 2 divided by the gamma function of n over 2 plus 1. This gamma function I remind you it's just the analytic continuation of the factorial. That's gamma of n is equal to n minus 1 factorial. That is for integer n is defined this way, and for complex n it's just an analytic continuation from those points. And there is a well-known integral representation for this function. So for n integer, it's just a factorial. For n half integer, you have gamma of 1/2 is square root of pi. Gamma of 3/2 is square root of pi over 2. And gamma of 5/2 is 3 pi over 4. So using this, you can verify that C1, C2 for 2 is a pi. So this is pi r squared, which is the area of a circle. C3 is just equal to 4 pi over 3. And in 4 dimensions, you get pi squared over 2. So a sphere in 4 dimensions has a volume of pi squared over 2 times the radius to the 4th power. So this is just mathematics. And now let's plug this in and calculate the entropy of an ideal gas. So, we would need that is S of E and B is equal to K log gamma E. So we'll need the log of gamma E, and we have computed this. We have obtained the sigma. So gamma E is equal to delta E times delta. And if I just differentiate the result I get up there, I get b to the n power times c of 3n times 2me to the 3n over 2. No, this is sigma, so I have the DDE times this times delta. So I get v to the n power c3n 3n over 2 times 2me to the 3n over 2 minus 1. And we can neglect this because n is going to go to infinity. So now I just take the logarithm of this and get the entropy. To get a log, to take the log, I need the logarithm of c. And log Cn is equal to n over 2 log pi n over log pi minus the log of n over 2 factorial. And n is going to be very large. So we use the Stirling approximation. I'll remind you, this is a very useful approximation. We will use it again. Which is that n log n, that n factorial is equal to n log n minus n plus a constant term. This constant is 1/2 log of 2 pi n, and we can usually neglect it. And so usually this is a good enough approximation. It's a very good approximation for n greater than 5 or something like that. And therefore log of c of n is equal to n over 2 log pi minus n over 2 log n over 2 plus n over 2. Then you substitute all the n and you find the entropy. And I think I will skip all the algebra. You just plug it in, you get the entropy. Let me just write the answer and look at the answer. Now you notice that this definition of gamma E as a volume in gamma space is defined only up to a multiplicative constant, because we have not specified the unit to measure it. So this entropy is only defined up to a constant, up to an additive constant. Which is arbitrary. Later, this constant will be fixed by quantum mechanics, but in classical physics, it is a constant. So now we plug everything in. I'll just quote the answer. And the answer is S of E and B is equal to n times Boltzmann's constant times the logarithm of V times E equal to n to the 3/2 power plus a constant. When you derive all these log pi's, if it's a constant, I'll just throw it into that constant. And this is the essential part. So this is what we get from the classical microcanonical ensemble. I want to look at it because there's a problem with this formula. There's a very deep problem. And that's known as the Gibbs paradox. That's a very, very deep paradox. And I'd like to talk about that. The Gibbs paradox shows that there's a problem with this formula, and that even at high temperatures, you know that you need quantum mechanics. That paradox is fixed only by quantum mechanics. Where does this come from? It comes from this term. But there's a problem here. This should be V over n. There's a missing n here. This should be one with a density, but it's V here as we derive it. And without this n, you get a paradox. Let's just review that. Suppose I have two gases. I put it in two compartments. Suppose these guys are different. Suppose so this is V1, V2, N1 here, and N2 here. Suppose I put in one part, suppose I put argon, and here I put neon. Two different gases. Suppose I withdraw the partition. Then the volume of V1 plus V2 is N1, N2, N1, but the argon and the neon can now move all over the volume. Here they restrict each volume. So you would expect that the entropy of this side would be bigger than this because they have more room to move in. And the difference in entropy is called the entropy of mixing. So in the first situation, entropy of mixing it is the S of N1 plus it is S final, the final state here, minus S initial. That being the final state, and it's called delta S. Since we have the expression for entropy, you just can compute it. And you find that it is equal to N1 log V over V1 plus N2 times log V over V2. It's always greater than 0. And there's no problem with this if you have two different gases. Because, as I said, if you withdraw the partition, each gas has more room to move in than before. So there should be more phase-space volume. As a consequence, there should be more entropy. And you can measure this, and it's correct. The paradox comes when the two gases are identical. So this is no problem. This is correct. When the two gases, but if two gases are identical, so before you have this, you have argon and argon there, and then later you have argon. But we don't have partition. But this formula doesn't know whether the two gases are the same or not. You get the same answer. Get the same delta S. And this is a paradox. Because if the entropy would increase just by withdrawing a partition, then the entropy is not well defined. Then it depends on the history of the system. If this system came from inserting 10,000 partitions, I withdraw them, the entropy will be 10,000 times what I thought it was be. So this is nonsense. It makes the entropy a not well-defined quantity. But we know experimentally that when you withdraw the partition, the entropy doesn't change. That is, delta S is 0 when two gases are the same, and that's the Gibbs paradox. Experimentally, delta S is equal to 0 when gases are the same. This is quite reasonable, right? You have air on both sides. You withdraw the partition, the entropy doesn't change. Boltzmann fixed this by saying that what you should do is to divide that V by N. And it's called correct Boltzmann counting. Boltzmann's fix. Is let S of E and B be equal to Nk log V over N times E over N to the 3/2. You put an N, you just stick an N in here. And this is called correct Boltzmann counting. Now you will notice this solves the problem, because here this log depends only on the density of particles, not on how many particles there are. It's the density. If both sides have the same density to begin in the beginning or after, this factor doesn't change. And this n just becomes n1 plus n2 is total n. So this putting in this factor solves the problem. When the gases are different, you do get this, and when the gases are different, you get 0. And that's called the correct Boltzmann counting. And people didn't know why. It just works. And now, of course, in hindsight, we know that it is because the argon atoms are identical at quantum mechanics. So when you withdraw the partition, they don't have more space to roam in because they're identical. You cannot tell which is which. So this is a profound paradox in that even in the classical domain, you notice that you need quantum mechanics. Without that, you get a paradox. But this recipe of the correct Boltzmann counting is not really a consistent recipe. You really have to go to quantum mechanics to see it come out. But in the meantime, when you do classical statistical mechanics, you always append this as a recipe. Otherwise, you get something wrong. So in order to illustrate this, let me derive this in another way. I derive the same result in another way, which is probably more illuminating. I will not derive the same thing. using a different method. So again, microcanonical example, I do not directly do this integral, but I do it with a different method. Now, gamma E is a number of states of the system with energy lying between E and E plus some tolerance delta. The way we did it before is just to integrate the Hamiltonian, since the Hamiltonian says that the energy is the sum of squares of momenta, we just take the volume of an n sphere. Here we'll just count states. We'll count states. So this is a different method. Method of counting states. And this is very useful because this method generalizes to quantum mechanics. So in the method of counting states, we take the spectrum of the particle, which is p squared over 2m, the energy spectrum, which is continuous. We chop it up into cells. Cell 1, 2, 3, 4, 5. And in each cell, the momentum is P1 at this point, P2 at this point, and then you take the momentum at the center of the cell as the momentum of that cell. This is momentum. The energy we say epsilon 1, epsilon 2, and so forth. And now we just say that how many particles are in each cell. The state of the system is determined by saying how many particles in each cell. That is, it is specified by a set of numbers called occupation numbers. Because it's N1, N2, and so forth. So the state of a system, state of ideal gas, this is an ideal gas we're talking about, is specified by the collection N1, N2, the collection of occupation numbers, which we'll just use the notation N. In mathematics, this curly bracket means a set. And so the curly bracket of N is just a set of occupation numbers. And of course, they must obey some constraints. Namely, the sum of all n is the total number of particles. And the sum of Ni times epsilon I is the energy of the system. Now we don't need a tolerance anymore because of this. The cell is a tolerance. Give us a certain tolerance in energy. It is in this second statement that we specify the ideal gas, because if the energy is the sum of all the energies individually, that means there's no interaction between particles. So this statement says it's an ideal gas. So what is gamma E? Gamma E is the number of states satisfying these constraints. In other words, it's a number of okay, so since we're cells, so what we do is we have n particles. So this is equal to, first of all, is sum over the set n of, say, Wn. Wn is the number of ways I can assign, these n particles in the cells given a certain occupation number n. And then I sum over all possible occupation numbers. So what is Wn? Wn is a number of ways. Suppose you have these cells, and you have n marbles. and they're distinguishable. You try to put the marbles in those cells. How many ways can you do that? Given that in each cell there's in N1, in the first cell there should be N1 marbles, in the second cell there should be N2 marbles, and so forth. And so W2 is the count of how many ways you can do this. And then gamma is the sum of all possible choices of occupation numbers. So we're doing classical physics, so we have to treat those particles or marbles as distinguishable. So if I put one marble in cell 1, another marble in cell 2, if I interchange them, it's a new state. Because according to classical physics, they're distinguishable. Therefore, Wn is equal to, first, I throw all the particles in and I permute them. That's n factorial permutation. However, when you permute two of them in the same cell, it does not give something new. Therefore, I have to divide by n1 factorial, n2 factorial, and so forth. And that's Wn. And now comes the correct Boltzmann counting. Says that you must replace this by 1 over n1 factorial, n2 factorial. That you have to erase this n factorial. Now, that doesn't make any sense classically, but that's the recipe. This n factorial is the origin of that Gibbs paradox. So when you do count things classically, you just have to omit this n factorial. That's the correct Boltzmann counting. So when you do this, you get S is equal to K log omega n. That is, omega n is equal to 2. Sum over, K log sum over all n omega n. That's the entropy. I want to do this because I'm going to illustrate a very important step. That's the next step. Because you cannot do the sum. You cannot possibly do the sum. You can probably do it for 3 particles. You certainly cannot do it for 10 to the 23rd particles, even with a computer. That's because the sum of all n's is not as simple. You have to obey the constraint. So all these n's are not independent. However, we are interested in a thermodynamic limit. And then we can approximate an approximation. That S is dominated by the largest term in the sum. S is equal to K log of summation n of n bar. This plus all the log n. Where n bar is the set that maximizes W. That is, you take this sum and just keep the largest term. And this works because we have a lot of particles. How do we know this is correct? We'll do this, and then we'll do proof. This is correct by calculating fluctuations. Usually, what does it mean? That if we just take one term and we calculate fluctuations from that term, you will know, you will see what we mean. And then if the fluctuation is small, then this is the correct answer. So we'll do this. So now we'll maximize W. by varying the set of accuracy numbers n subject to the constraints. Now, since maximizing the log of W is the same as maximizing W, we just maximize log W. Which is equal to summation over I minus log Ni factorial, which is equal to, using the Stirling approximation, minus summation all the cells of Ni log Ni minus Ni. Plus. Is it plus or minus? Plus. Which is equal to minus I Ni log Ni minus n. But you're subject to the constraints. This means that these NIs are not all independent. In order to make them independent, we use the method of Lagrange multipliers. That is, you take Wn, log Wn, instead of varying this, instead of equal to 0 to get a maximum, you append a n minus b e. These are the constraints. And you say this variation is equal to 0 by varying each n independently. Then later you determine these alpha and beta at the end in order to satisfy the constraints. And those alpha and beta are called Lagrange multipliers. So I do this. The n term, the capital N term, vanishes upon variation. So this is equal to the variation of minus summation I Ni log Ni minus alpha summation Ni I minus beta summation Ni epsilon I is equal to 0. And now I can treat each Ni as independent. So by varying this independent, I get minus, for the first time I get summation I get log Ni, and this thing will plus 1 times delta Ni, which is factor out, minus alpha log delta Ni minus beta epsilon I times delta Ni is equal to 0. Therefore, since delta Ni, the delta Ni's are independent, log Ni plus 1 must be equal to minus alpha minus beta epsilon I. And this gives you, this is n bar. And therefore n bar, Ni bar, is equal to e to the minus alpha minus beta epsilon I times some constant. And of course, this is Maxwell-Boltzmann distribution, as you all know. And you determine alpha and beta by applying the constraints, which is the way we determine those constants in the Maxwell-Boltzmann distribution anyway. So it's even, I can even write it. It's equal to C0 times e to the minus beta epsilon I, because alpha is a constant. So Ni is equal to this, and epsilon is I cell. Now, how do I relate this to the distribution function which we were using in deriving the Boltzmann transport equation? These are the occupation numbers on the I cell, so relation to the distribution function. The distribution function at pi in the I cell times the 3pi, this is a volume element, is equal to Ni. By definition, right? Because Ni is the number of particles in that cell which has a volume of d3p. And therefore, say, for example, summation I Ni would be equal to integral d3p f of p. And summation I Ni epsilon I will be equal to integral d3p p squared over 2m f of p. And determining the alpha and beta is the same as determining the constants in the Maxwell-Boltzmann distribution that we have done. So this is probably a better way of deriving the result. Having done this, I just plug this back into W, and I just plug it in this formula to get the entropy. You get the same entropy we calculated for the ideal gas. So you get the same thermodynamics as before. However, here I've merely taken n to be the occupation number that maximizes Wn. And I say that that term dominates the sum. We have to justify that. To justify that, we have to show that almost all Ni's have the Maxwell-Boltzmann distribution. That is, this condition is the most prevalent condition. That is, here we have to sum over all choices of n. We're going to show that if somebody puts different n's in a bag and you blindly say you pull one out, it's bound to be Maxwell-Boltzmann. And that's why the Maxwell-Boltzmann dominates. To do that, we will compute the average value of n and the mean squared fluctuation of n in this ensemble, and show that that's very small when n gets large. And then, of course, the mean squared the mean n will be coincide with this is not the mean n, this is the mean that maximizes it. Now we define the mean value. And these two will coincide when the fluctuations are small. So the technique of doing this is also very general, and so it's very useful. So, ensemble average. If I have of, say, quantity O ensemble average is defined as O, which depends on n, which could depend on a calculus. So it's O times Wn sum over n divided by sum over n Wn. This is ensemble average. So we will define the average occupation number. Say the kth one. This is defined as you take the kth occupation number multiply W of the set of occupations which contains k, of course, and you sum over all possible sets. And use summation W. Yeah. Then, of course, if you nk squared minus nk squared is the mean squared fluctuation. This is the fluctuation. You average nk squared, this is the average of nk squared. You'll notice this is also equal to nk squared, nk minus nk average squared average. Because just look, if you expand it, you have average nk squared minus 2 nk plus nk squared average. So the first term, the first thing will be nk squared average. Here, this is a number, so you put it, so it's a minus 2 nk squared plus nk squared. So this cancels, so you get back. So you can either write it this way or this way. We're going to show that this is small. When n goes to infinity. If this is small, then almost all nks will be the average value, because the deviation from the average is very small in ensemble. So let's calculate. To calculate this, we use the following technique to calculate this, which again a very useful technique. You go back and you redefine Wn. We have already removed the n factorial by the correct Boltzmann counting, right? You define it by putting some, say, g1 to the n1 power, g2 to the n2 power, and so forth. You could think of hg as an intrinsic probability of that cell. But then this is just a mathematical device. Later, we're going to put gi approach 1 eventually. So we just put it here to facilitate calculations. Okay. Notice that I will take Wn. If I differentiate with respect to the kg, I just bring down a power of n. So I'll just get nk. And if I multiply again by kg, I restore the thing. So this just gives me nk times W. And therefore, average nk is just equal to the gk times gk of log W of n. Because if you log, because if I divide by n on both sides, I get a difference of log. Right? And this is also, it can be written as d by d nu k of the log of w of n, where nu is defined as the natural log of g, log k. So also all I need to know is know the log of this. But when I do the differentiation, I get the average value of n. I can also very easily get the fluctuation. Consider the following calculation. Let us compute n k squared average. That means I have to pull down 2 powers of n from the w. So this is just equal to, summation, let me write down, summation n k squared wn times summation w of n. Or this is equal to 1 over summation wn. Here I have to put on 2 powers of nk, so I have d nu k squared times log of w of n. But one differential brings on 1 power. I do it twice, I bring on 2 powers. And to save right now, I'll just call this gamma. I just call this gamma. That this gamma n, but so this is just equal to 1 over gamma times d nu k squared of gamma. This is equal to d nu k. I bring this out. 1 over gamma times d gamma d nu k minus d nu k of 1 over gamma times d gamma d nu k. This term is just equal to d nu k of d nu k of log gamma. The second term is just equal to plus, since 1 over gamma squared d gamma d nu k times d gamma d nu k so this whole thing is just equal to d nu k d log gamma d nu k plus 1 over gamma d gamma d nu k squared, which is, as you notice, just equal to d nu k of the average value n plus nk squared. And therefore, you have a formula for the fluctuation. I just bring this to the other side, and I get nk squared average minus nk average squared is equal to d nu k of nk. But nk is a Maxwell-Boltzmann distribution, so we can do the derivative. Since nk is equal to g of k times some constant, times I mean as beta epsilon k. So d eta d nu k. What is g? G is just e to the nu k. So it's e to the nu k. So this is just equal to nk. And therefore, our fluctuation formula says that the mean squared fluctuation of nk minus nk squared is equal to nk itself. Now you see that this is very small because each term on this side is of order n squared. And this term is of order n. So this is negligible compared to the other terms. In other words, if I divide both sides by nk squared, I will get 1 over nk. And this side is of order 1, and this side is equal to n over nk, which is of order 1, times 1 over n, and approaches 0. That's a rather remarkable result. It just says that if somebody has a bag containing all possible occupation numbers and asks you to draw one, you're bound to draw one, you are bound to draw a Maxwell-Boltzmann distribution. And when n goes to infinity, you are certain to get a Maxwell-Boltzmann distribution. And that's why the Maxwell-Boltzmann distribution is dominates that sum that we use in entropy. And the smallness of fluctuation underlies the validity of all of statistical mechanics. And it depends on a large number of particles. So now this is an example of how you use the microcanonical example to derive things that you already know, that we derive from Boltzmann equation. This is a different way of deriving things. And you will see that this way of deriving things never mentions collisions, no cross-section. It gives you the equilibrium answer, but it does not tell you how long it will take to get here, to get there. But you will notice that this is a very clumsy method. This is the ideal gas. If I don't have an ideal gas, it'll be very hard to do things. So we will need a more efficient way of computing things, and that will be the canonical ensemble, which we'll discuss after the break. We'll take a break for 10 minutes.